I'm going to be talking today about the detectability of various geological targets using airborne gravity meters. And this is an airborne gravity talk, not an airborne gravity gradient talk, differing from most of the ones we've seen today. Pretty standard presentation outline. The interesting part, the meat of the talk, are a number of case studies where I'll be presenting the results from some airborne gravity projects. So all of the data that I'm going to be showing today has been acquired with our SGL airgrav system. This is a system that we designed and developed and have been flying for over a dozen years now. It's a 3-axis gyro-stabilized platform with 3 accelerometers. This allows us to record vertical gravity as well as the 2 horizontal components. As with all airborne gravity, what people are interested in is derived from the inertial accelerations as measured by our gravimeter minus the GPS accelerations which model the aircraft movement. Our system has been designed to tolerate normal daytime turbulence, and thus the dominant error is the accuracy of computing the aircraft movement from the GPS accelerations. However, now this is a chart that you may have seen, or a variation of this chart that you may have seen presented at in other presentations over the years. To note is on the y-axis is the gravity amplitude, on the x-axis the half wavelength resolution. When I'm talking about resolution and filter length and so on from now on, I'll be talking half wavelength all the time. The red dashed line is something that was presented in a paper by Van Kahn in 2004. It was called the GPS limit, which was a theoretical limit for accuracy of airborne gravity. And the theory was that for airborne gravity you could only expect to acquire data that is to the up and to the right of that line on the chart. So the big red dots are various well-known geological targets, Broken Hill, Olympic Dam, etc., etc. And in those cases, the gravity amplitude means the amplitude of the signal that you would expect to acquire if you were flying over one of those targets. The rest of the little dots and stars and plus signs, etc., are all values that come from our surveys. So those are the accuracies that we have computed on, these are all projects that I'm going to be presenting in this presentation. So the theory is that for any of those projects, we could have detected anything that's up and to the right of those little dots. So why are there dots all over this graph? We've got one system, the SGL airgrav system. Why isn't there just one resolution and one accuracy that we can obtain? Well, the reason for this is that survey design is a huge factor in accuracy and resolution. So first of all, most of the surveys are done oversampling the data. That is to say, we have a close line spacing and we filter the data, and the tighter the line spacing, the higher accuracy you can expect. So that will bring the points down on that graph. We also fly in different aircraft and with different speeds, and because we're acquiring at the same sample rate, our airgrav data is acquired at 128 hertz, so that rate varies in spatially along the ground depending how fast you're flying. So the slower you fly, the more to the left on that chart you're going to be. Also, and this is a small thing, but we're getting better at it. So mostly due to GPS and gravity processing improvements and some small hardware improvements, we're doing better now than we used to. So if you look at the points in the top circle, those are the accuracies at various resolutions from the test line that we fly close to our office in Ottawa that were flown in the year 2000. We've flown that test line now somewhat over 250 times. The bottom one is the results from, at the same resolution, from when we flew it last year in 2015. So you can see a small improvement there in accuracy. So when I talk, how do we calculate accuracy? Well, normally for a survey project, we use the even-odd grid technique. So this way we assume that the line spacing has oversampled the area. We compute two completely separate data sets, one using all the even-numbered lines, one using all the odd-numbered lines. And then we just subtract the two and call that, or half of that, the noise estimate. Now this, of course, is an upper limit for noise because it may include some signal that's not on adjacent lines. You can also use repeat lines, and as has been talked about earlier today, comparing to ground gravity, which has some problems. For instance, it includes ground data errors, and there may be processing differences. First case study. I'm not actually going to talk about this one very much because Ian did it very nicely for me already. And also there's a poster out there that some of you have seen, and if you haven't seen it yet, please come after the presentations, about when we flew the R.J. Smith Cowering test site. So we flew the bigger airborne gravity area, but we also flew the inner AG area at a 50-meter line spacing. And the resulting data at a 600-meter filter length, we think is a really excellent result for this teeny tiny little survey block, which would generally be considered the kind of thing an AGG system would fly. But we flew it anyway since we were there. This is one version of what we were measuring. This is from Martinez and Lee, showing the values greater than 1 gram per cc of what you're measuring. Again, a very small volume close to the surface, usually considered an AGG target, but as shown in the previous slide, was able to be well imaged with the airborne gravity data. So on the chart, the little dot, the green dot in the lower left circle, that's the accuracy and resolution from the inner area, the 50-meter line spacing, 600-meter filter length with a 0.24 milligal accuracy. The other circled one is from the outer area, which was flown with a 200-meter line spacing, ending up with a 1 kilometer resolution and 0.34 milligal accuracy. Just a side note here that detectability really depends on what type of geological structure it is you're looking for. So, for instance, a sphere, like we saw in the volume from the inversion of the Cowering data, which in this example, an 800-meter radius sphere at 2 kilometer depth has about a 1 milligal signal. Very detectable. It has about a 10 atvosh signal, so also very detectable with an AGG system. Something that has less of a gradient, like for instance an offset fault, at the same depth, a 2 kilometer depth, and a 100-meter offset, the same density contrast, still has about a 1 milligal signal, but somewhere down around 2 atvosh, maybe a bit less, in the gravity gradient. A project that we flew in southeastern Australia, the Gippsland Basin, was flown in a very well-studied oil and gas area. You can see the survey block outlined in blue there. It was flown with a 1,000-meter line spacing and a few infill lines at 500 meters. The gravity data allowed us to do a detailed interpretation of the major structural features within the basement and also to improve the understanding of the basement configuration. So the Bugey gravity grid on your left. You can see a low over the central deep basin there. You can see gravity highs over the, I believe it's called the North Shelf and the South Shelf. The vertical gradient in the middle has white lines drawn on it which come from the peaks of the horizontal gradient, the calculated horizontal gradient of the gravity data. And that really shows a good definition of the faulting within the basement, or the structure within the basement, and also the faults, the Foster Fault system and the Lake Wellington Fault in the north. So these, I'm showing a number of accuracies and resolution for this Gippsland Basin survey. The 1,000 meter line spacing, slightly higher than the 500 meter line spacing as you'd expect, and using filter lengths between 1,500 meters to 4.5 kilometers, you can get resolutions, accuracies from about 0.3 milligal down to 0.1 milligal. We flew a project in Colombia, and the interesting, well, one of the interesting things about this project is we flew it with a helicopter, but at a very high ground clearance, or high for us anyways, 1 kilometer ground clearance. This was done for security reasons. The purpose of the survey was to get a better understanding of the complex geology in this area. It's in the Andes. The Cauca Basin is between the Western Cordillera and the Central Cordillera. So the gravity data was used to refine the depth and location of the subbasins within the Cauca-Patia Basin. And in this area, the sediment thickness is up to around 3 kilometers. The data was also used, obviously, for some major structural interpretation, but also that high-pass filtered Bugey gravity data was one of the things they used to define a number of zones that they were going to use in determining where they would do future seismic acquisition. So the white lines there define the area into define the block into 4 different areas, and they use that then later when planning seismic acquisition. In Peru, we flew this is a more standard petroleum acquisition project with 800 meter line spacing at 150 meter altitude. And I'm sorry to continue on with these numbers about line spacing and height, but the point of this talk is that these things are really important. It's kind of boring, but this is what makes or breaks a project. So they did have some seismic data in the north of this block, and from that they knew that they knew the location of 2 faults. I believe they're called the Cameo Oeste and the Cameo Este faults, and you can see those quite clearly in the gravity data in the center and somewhat less in the mag data. But what they used the airborne gravity and airborne mag data for was to extrapolate where these faults continued into the south of their project area where they had no seismic data, and then they would decide if they were going to do more seismic acquisition based on that. And as a sort of standard petroleum project, it's got kind of a resolution and amplitude more or less in the center of this graph, or in the center of the points of the graph. So this is one of my favorite projects. It's a mineral exploration project that we did in the Timmins area in northern Ontario. It was a helicopter survey, which we talked our helicopter pilots into flying very, very slowly, Well, we didn't talk them into it. They wanted to do it, although at the end of the project they said that was maybe a little too slow. And it's 55 kilometers an hour. If you can think of what it's like to drive your car at 55 kilometers an hour, it's very slow for an aircraft. Flown, we did 6 blocks over areas of interest for F&X mining. And the idea was to directly detect the known or dense ore material to define where the extent of these deposits. And on the right, you can see the Bouguer anomaly grid draped over topography, and it does show a good image of the geology in the area, which included, in this case, that's the Podolsky block, a working mine. So there's been extensive drilling in this Podolsky block area, Podolsky property, and so they have a pretty good idea of the extent of the mineral deposits that are there. And so confidence was built by the good correspondence between the modeled gravity data and the acquired gravity in this area. And I'd just like to mention that none of these bodies have any dimensions greater than 1 kilometer. So we're talking about pretty small volumes here. So these are the points that are way over on the left and way down on this graph, because we were flying very tight line spacing and very slowly. So with a filter ranging from 250 meters to 450 meters over all the blocks, the range in accuracy is from about 0.2 to about 0.65 milligauss. We also, on one of the blocks, were able to do a comparison to some ground gravity data, coming up with a 0.56 milligal accuracy at 300 meter resolution. On the other end of the scale are the projects that we've been flying with NASA since around 2008, I believe, which was the International Polar Year, was our first project. These are very different in that we put our gravimeter in with a whole pile of other instrumentation that other groups provide to NASA in a big aircraft, either a DC-8 or a P-3, or I think it was done with a Twin Otter in Antarctica as well. They fly really fast, up to 800 kilometers an hour, and huge range of altitudes, from 150 meters up to 12 kilometers in altitude. And 12-hour flight lengths where they can acquire about 9,000 line kilometers of data. So that's, yeah, it's pretty impressive. So the images show the acquisition of the Icebridge missions from 2009 to 2014. We actually flew Icebridge again this year. We will be flying out of Punta Arenas this fall and are contracted to fly again next year. The one in the middle is the Arctic, and it's kind of a strange view, but it's Greenland on the south and Alaska up on the top, and North America sort of heading off to the side. But it's really hard to show the North Pole on a map. The bottom one is Antarctica, and almost all the flights are flown from Punta Arenas, Chile, so that's why you see that sort of cone of data coming out of Punta Arenas. So the purpose of the gravity in these projects was to calculate bathymetry, because the ice penetrating radar doesn't penetrate the water. So underneath the ice shelf, they use the gravity to calculate bathymetry. Under an ice sheet, so on land, sometimes the ice penetrating radar gets confused if the ice is broken or saline, and so then the gravity helps to define the topography under the ice. And in one particular and very beautiful application of that, this is an image that was made from the air gravity data of the Gamburtsev Mountains, which are on Antarctica. And they're huge mountains, kind of like the Alps, but they just happen to be under 3 kilometers of ice. So these points, of course, are way off to the right and fairly high up because they're flown really fast, and also they're not flown in grid format. These are mostly acquired as lines. So these accuracies are computed from repeat profiles wherever they happen to fly the same place twice or 3 times. Then we could use that to calculate some sort of an accuracy. And using filters from about 5 to about 9 kilometers have accuracies about 0.5 to 0.7 milligauss. So some general conclusions first of all. Detectability is highly dependent on the type of geological structure that you're measuring. Airborne gravity resolution and accuracy has improved far beyond the theoretical GPS limits that are often cited. And in order to do that, proper survey design is required. As far as detectability, I've shown applications where airborne gravity was used to resolve a deep basement structure, major faults, basin bounding faults, subtle structures within a sedimentary section, shallow deposit type structures, bathymetry, and sub-ice structures. And it can be used for depth to basement interpretation, reprocessing, and planning seismic acquisition, amongst many other things that everybody knows about. So thanks very much to the companies and organizations that allowed me to present this data today. Also to my co-authors and all the other people at SGL that were involved in acquiring, processing, and interpreting this gravity data. Thank you.
Okay, well, it was great to see a talk on airborne gravity after all the talks on airborne gravity gradiometry. But returning to the airborne gravity gradiometry, next up we've got Kit Campbell. His professional life encompasses since he was 16 years old, more than 40 years of diverse experience in all facets of airborne and ground geophysics. He has both contributed to and directed diamond projects throughout Canada, Australia, Africa, and Russia, as well as metal and petroleum projects in the USA, Latin and South America, Africa, and Middle East. Mr. Campbell specialises in applied geophysics for kimberlite exploration and the integration of those data sets with geochemistry and geology in order to define and prioritise the drilling and delineation of realistic targets in challenging environments. And Kit will be, I believe, giving us an overview of a variety of the projects that he's worked on. Over to you.
Okay, a couple of things. In your outline, the word petroleum is mentioned. There won't be any petroleum discussed in this, which is a pity, I suppose. I had some nice examples all in the East Africa Rift, but I can't tell you anything new that you don't already know about. Not much of a story to tell, and sketchy permissions. I'm going to discuss, give you sort of 2 stories, but there's a common thread. And the thread here is, I hope, that acting as a consultant or a client rep in collaboration with a contractor, I believe we've improved the end product. So that's my story. It's not a case history. There's no interpretation. Outline, I'm going to give you a AGG survey for kimberlites in the Slave Province of Canada. I'm going to talk about what we feel was a rather innovative approach to establishing the bathymetry corrections, and then quickly going on to a second survey, but discuss 2 topics: the critical importance of terrain corrections, and then also get some assessment of the tensor component calculations, and hopefully some coherent conclusions. A motivation. What do we want out of the survey? Well, clearly we want to find an anomaly that indicates what we expected to see of an ore deposit. That's going to always be a multi-stage process involving planning, acquisition, data processing, data review, interpretation. As a client rep, we can probably have some input into planning, which is always a balancing act between the technology and ultimately how much budget we're allowed to play with. Acquisition is, acquisition, is the contract being flown to various specifications and whatnot. Data processing, particularly in AGG, is going to be at least semi-proprietary, if not wholly proprietary, and we don't really get to, it's just given to us and we have to deal with it or accept it. Data review. Data review is probably the first chance as a client rep or a consultant. Ashbourne knows what I'm talking about. It's the first chance we get to look at the data and see what there is, and that's invariably when the client is on our case right away. What do you see? Where do we drill? Well, wait. Interpretation is when it's all put together. It's really exciting, but I'm going to talk about just and most of the case studies here or at any meeting will talk about the we're going to go backwards and just look at the data review and then try to discuss something about data processing. The data processing flow in AGG is quite complex, but it has been simplified and described by Dransfield and Lee. The actual AGG compensation, as I just mentioned, it's not available to us. It is what it is. There's terrain corrections, and then there's gradient component transformations. The data review, I think that's the first chance someone like me has an opportunity to involve myself and look at that data, and does it make any sense? The first thing we look at, does it make any sense? Is it match what we know or what we think we know about the geology? Okay, first survey. This was flown in 2014 in Margaret Lake for a company called Margaret Lake Diamonds. I hope you can see it. There's a little red dot right there. So it's about 80 kilometers north of the east end of Great Slave Lake. It's in the vicinity of, actually it's bounded to the south by two significant properties. One being the Gaucho Quay mining leases. That's under active mine development right now by De Beers in joint venture with Mountain Province. A spin-off of Mountain Province is Kennedy Diamonds. They've got some kimberlites that were not discovered with gravity gradiometry, but they have been well mapped by they've been well mapped by gravity gradiometry. Based on those results in close proximity to the Margaret Lake Diamond property, management decided to go for fairly aggressive and decided to go straight to an AGG magnetic survey and forego the more common frequency domain EM and magnetic survey, which would be a more common approach in the Slave. As you may or may not know, kimberlites in the Slave are typically, well, actually exclusively to my personal knowledge, create gravity lows. They're also commonly, but not exclusively, covered by lakes. Therefore, we're going to have bathymetry control. In our particular case, about one-third of our property was covered by lakes. In fact, we counted them up, 1,068 lakes, 80 square kilometers of water on a property. Varying depths, we don't know how deep they are. Conventional methods of bathymetry are costly, time-consuming, and inherently they have their own errors, and I submit those can be very significant errors in depth measurement. So the client recognized the need for survey-wide bathymetry control, and we wanted to build that into the DEM and provide that to the contractor so they could be incorporated into a true 3D terrain, what I call 3D terrain correction. We contracted sorry for all the text there, but we contracted a spatial imaging company called Oracle out of Victoria region, Vancouver Island, and they used Worldview 2 panchromatic plus an 8-band multispectral imagery, and they had to derive a modification to a published algorithm by Stumpf and Holderried, and it essentially relates spectral radiance values to ground truth information in order to derive depths for shallow water regions. All the water bodies within this region of interest were identified and modeled at a 2-meter pixel resolution, and this is we'll call that an optically derived bathymetry model, or an optically derived DEM. We ended up with 2 grids, if you will. One was I suppose there was 3. A DEM of the surface. We had a DTM, which included the basin, including the bottom of the lakes, and then we had a 3D model of the actual floating lake bodies. We needed, unfortunately, we needed 2 scenes to cover the whole property, and that created some issues, as it turned out. Unexpected to certainly us. So we ended up with a elevation accuracy of plus or minus 2 meters within a 4-meter radius area. Now, as I said, conventional bathymetry, we had access to very limited bathymetry that had been earlier collected by a good contractor, Aurora Geoscience out of Yellowknife. Not on our behalf. They collected bathymetry on some lakes on property they didn't own. But anyways, they collected and we had that data. Using depth sounder and Zodiac inflatables, they acquired that over 2 summer seasons. And we used that as the initial calibration for the optical bathymetry. You got to recognize that the accuracy of the multispectral imagery, or the bathymetry derived from those satellite images, is directly related to both ground truth data and the water depth. Also, I'd say the clarity of the water depth of the water, with accuracy reportedly decreasing substantially in water depths once over 20 meters. It becomes kind of iffy. Even in these lakes, the scenes that we acquired or the scenes that we obtained were acquired in August of that year. So we felt we had very clear water. Probably the lakes were a bit lower than they might have otherwise been, but lower in elevation. One of the issues when I compare these results, one of the issues in the processing, and I had never really thought about it until it was starting to be done. The surface of the lakes is not the same. It's not like sea level. The surface of each lake is different from the lake beside it, and that caused that alone added 3 months to the working up the optical bathymetry. That was a tricky. I don't think well, certainly this contractor, Oracle, who seemed to do a lot of work, they had never come across that issue before. We had 2 lakes on the west side of the property on which we had a very good sonar coverage. The lake in the bottom there, I call these the West Lakes. The lake in the bottom was essentially all covered with sonar. The lake in the top was covered at least out to the property. It was covered further, but I couldn't get it because that little red line, if you can see it, the little red line over there, that's the property boundary right in here. So that's our data that I could get was cut off. At least it was cut off at the time we did this comparison. The color bar scales on the 2 left images are the same. If you can read it, roughly 0 to 9 meters depth, and then the difference grid on the right, which is its own color bar. You'll see that on the southern lake, it's pretty good. Good agreement. The optical has mapped the depth approximately 2 meters shallower than the sonar. And I feel that at least part of that could be that this is from 2014. The inflatable data was collected in 2012 and 13, or 11 and 12, I actually forget right now. So water up here, the lakes will change. We did have a big, okay, that doesn't work. The major difference was right in here at this arm, and that's a difference of about 8 meters. Now, we didn't see anywhere else in the we did have some other lakes with sonar. We never saw a difference of more than 4 meters over the survey area. Unfortunately, this is right where I have two scenes, two WorldView 2 imagery scenes butting. So I'm suspicious that the joining of the satellite imagery scenes caused some of this error. I'm also, I really don't have any feel for the accuracy of the sonar data. We had nothing to do with collecting it. It was just given to us. So I'm a little bit iffy about that. However, look at the different stats. The mean difference is 0.6 of a meter, standard deviation of 1.64. I felt that was pretty good. The absolute accuracy of the sonar is not known. The resolution, though, is good. It's around 20 centimeters. What I also want, I should go back. Okay, something I want to draw your attention to. Now the thing with the sonar, it's not going to get to the edges of the lakes. You can see the 50-meter tracks, 10-meter sampling along those nominal 50-meter tracks. It can't go within, you can't get within about 2/3 of a meter of depth because the propeller shaft you'll break the propeller, and there's safety issues on the Zodiac. So they can't go up to the edge of the lake. Whereas, of course, a satellite is just going to go, you're going to get complete coverage. So I should have mentioned that. Okay, stats. As I said before, the largest single difference was in a somewhat localized location, and unfortunately, I don't have a hard and fast explanation for that. We didn't see it anywhere else. Now, quickly, before and after, right early on, we had picked out what we call ML001 target, small lake, 150-meter diameter. I really like the look of it. We had a magnetic disturbance as well in here, a break in the magnetics. So, this is really good. Gravity, magnetics, and is at the head of a significant kimberlite train, or it's at the head of the train, or no, it's at the head of the train. It was in a great location, so we're kind of keen on that. When we so this is the Fourier 2.67 GDD. It's terrain corrected using the laser scanner data from the Falcon system, but no bathymetry correction is in it. When we added the bathymetry, that anomaly more or less disappears. The optical bathymetry depth on that lake was 9 meters. And as those of you who do this sort of stuff, about a 1 meter change in water will cause adding 1 meter of water on a lake will add about 4 to 5 FLOS in amplitude of the signal. I draw your attention to this lake, weak anomaly, essentially just totally disappears once you put the bathymetry on it. Water out here is 4 to 5 meters deep on this lake. Didn't make a significant difference, but we were picking, I was picking a target there. So, quick discussion. We think this is the first time satellite imagery has ever been used in mineral exploration for establishing bathymetry control. Even with the 4-month delivery time, what I mentioned, we had initial results of the bathymetry within 1 month of signing a contract with the spatial people. But then as I said, we noticed, right away we saw this bust in the elevation, so we said that you got to go redo everything. We think we've learned from that. I feel that the next time we do this, we'll get a pretty good result, even with multiple scenes in 4 to 6 weeks delivery time. The addition of that bathymetry allowed us to proceed immediately and with much greater confidence to an interpretation stage. And I'm not going to show you anything else, but the drill targets, examples of the responses, those are all available online as a corporate presentation, April, on the Margaret Lake Diamonds Incorporated website. A second survey I want to talk about, we're going to have two strings in there, two strings of thought, terrain corrections and gradient transformations. This is flown for Canada Zinc Metals. I'm going to show you, they have two blocks. They're geographically separated. In the Kachika Trough, this is all SEDEX, lead, zinc, silver mineralization. We're going to talk about the Akai and the Mount Alcock U and North block. So the examples I'll show you will all be of the Akai. We know, previous work, we know we can use gravity to map these barite-rich zones. They're in association with the sulfides. Conceptual modeling here suggested we should see something like a 30 to ETVOS response. We also had the Iron Mountain survey, results of which were published and put in the public domain. Similar terrain, quite a bit south of this, but similar terrain. And we felt, yeah, we're going to see something, we should see what we want to look for. We should see the target that we're looking for at 30 to 50 ETVOS signal. Okay, and this data was flown in 14-15. Terrain corrections. I gotta race through this. Okay. First of all, when we got it, we had a quick data review, did a bandpass filter zone of interest. Results had minimal, if any, correlation with map geology. Just nothing. Didn't correlate. So what's going on here? They seemed to have a pervasive noise of around 20 ETVOS. We'd done our due diligence during the acquisition. We knew we had our instrument noise around 3.5 ETVOS for it. It was great looking data. So what's the error? Could be near surface density variations, errors in terrain model, incorrect density. So then we had to go back and look at the density corrections. We see this radial average power spectra. The free air is down in here. Okay, and this is a terrain correction. It's sort of a plateau in our zone of interest. Yeah, that terrain correction is bringing in signal. It doesn't mean if the signal is erroneous or not, but it's bringing signal in. The laser scanner used to generate the first EM, the laser scanner from the Falcon system, turned out it was adversely affected by, it was picking treetops and then some treetops, some not. The terrain model was, we were flying an aggressive drape, close line spacing. As you've talked, we weren't getting a swath, right? There was no swath. So it was incomplete. So, okay, we're going to use the trim data, BC trim data. It's supposed to be really, really good. And it's ground surface, 25 meter pixel. We compared to the LiDAR. Then the client turned out, and the client had a LiDAR, a true LiDAR survey over a portion of the Akai. We're showing a little cutout block of that on the left. There's around 300 meters elevation there. There's the difference. 20, up to 20 meters. Could that cause the difference? Does that cause my problem? Yes, it could. We feel it could. We calculated the GDE differences from the forward modeled LiDAR and the trim, and that's the kind of difference I was getting, the model difference, and that's pretty akin to what we were observing in terms of what I was calling it noise. This is my noise, okay? As an interpreter, this is my big noise. This is all in the paper. We calculated we had around 30 plus ETVOS error in this survey. And we put most of that down to the digital elevation model. We got through that. We still had some questions. At the end of that, we had a better data set, but we still had questions. So what's the noise? So we came up with an idea. Actually, Sean came up with the idea. As you know, there's 4 complements that the Falcon system is measuring, the A and B, NE and UV. So we just said, well, what's the noise? Let's look at the noise of those compared to the noise after the transform. Thank you. And I'm doing all this right now on free air, so I've kept we've kept the terrain issue out of this. Okay, those are the transformations, you've seen that. We compared it to the Margaret Lake survey because we had access to it. And we took the DIA survey, which is the trading symbol for Margaret Lake Diamonds, CZX trading symbol for Canada Zinc. We looked at the grading component in the case of the Slave, relatively flat terrain, great flying conditions, tight line spacing, everything went tickety-boo. We see a measurement noise in the NE and UV of, under 2.5. The Fourier estimates come down, equivalent sources come down. Great, everything's working. When we look at the Akai and Ewan North block, Fourier is over 20. Equivalent source does a much better job, but it's still struggling. Why? Raises some questions. So then we want to look at it line by line. We want to see, the measurement noise is really tightly confined, all within 10 FOS and almost all below 5, and it's isolated on, and the ones that are bad are just on 1 or 2 lines. Fourier is spread out across the whole survey. The equivalent source there is focused on a few lines only, and then we came up with an idea, well, where does it, my only complaint with looking when we look at the line-to-line estimation of noise is based on a line, and it doesn't matter if the line is 6 kilometers long, as these were, or 600 kilometers long. You get this one number. So we said, let's take 100 sample. I forget now why I used 100 sample, or why we used 100 samples, but we just did. So moving the windows, and then we did the same histogram. You can see in the NE, all the standard SD values in the measured data are below 10. Fourier are widely spread. Equivalent sources are focused on a few lines only. Okay, quickly. Sorry if I'm running late. So we take the NE and UV component we combined. We took the maximum of each of those 100 point moving windows. We'll take whatever was the highest, we took that one, and then that gives us a single value for the survey, and then we can grid that. And we'll look at again, we did this all with the DIA survey as well as the Canada Zinc survey to compare the two. The measurement noise, as you can see, is well below 5 FOS. The Fourier and equivalent source for CZX around 5, 2 times higher. In comparison, about 95% of all the DIA measurements are falling below the 5 FOS. So that single number, we could image it. This is for this is a piece of the Akai block. And forgive me, this is, I'm going to say this is about a 2 by 4 kilometer. Well, those are 200 meter space lines right there. So you can, there's more than 20 lines there. So the measurement noise is great. Fourier's not very good. Equivalent is pretty good. This is like a confidence level. So blue below 10, green 10 to 15, yellow moderately suspicious, red beware. Quick discussion. Equivalent source, it yielded much smaller errors than the Fourier. The Fourier being used, as I understand it, is, I didn't reference it, but it is referenced in the paper, is a modified Fourier, supposedly going to work in rugged terrain. We feel the equivalent source should have worked a lot better. However, a method of moving windows to examine those errors lets us isolate where we think we could interpret with some confidence, and it identified the areas where I just didn't want to interpret. I didn't want to go there. There was no definitive conclusions as why well, I think there is a definitive conclusion as why the Fourier processing failed, but there's no good, we didn't come to a definitive conclusion as why the equivalent source struggled. It could have been a combination of the low terrain clearance, aggressive terrain following, also the orientation of the survey reportedly caused some issues with processing. The orientation of the survey was not due north, south, east, west. It was oblique. Iron Mountain Range, similar, they didn't have a problem, but those lines are all flowing north-south, so I don't know, I'm gonna leave that to other people to figure out. I feel the conclusions, clearly the importance of the data processing and data review stages prior to the interpretation. We felt by working with the contractor, everything was pretty amicable. It took a long time, but we feel we got a much better product in the end. It just took a while to get there. Ashbourne's talked about it, Mark has talked about it, Louise has talked about it. We need good terrain models. The terrain models, we're sort of accepting what they are, and I've heard about the new gravimeters coming out. You're gonna, in British Columbia, we're gonna need a LiDAR survey. I think we're gonna need true LiDAR. Okay, and I've got a methodology to quantify and delineate the errors on the calculated grading components. And that's all. Attention should be given to all the ancillary measurements, and a couple of quick acknowledgements to the two companies for giving us permission, and also to Buddy for coming up with the actual idea to use the satellite imagery, and a lot of credit to Steve Saul for his persistence and patience in putting up with me, and putting up with us. Okay, and that's it. Thank you.
Okay, next up we have Tony Rudge from Rudge Energy. Tony studied a Bachelor of Science at Monash University, where he majored in Earth Sciences, graduating in 1997. Tony then went on to complete an MSc in Reflection Seismology at Monash University in 2001. After completing his MSc, he then moved to Perth to take up a position of Processing Geophysicist with CGG Australia. He has also held positions as a metallurgist at AMTEC and Senior Geoscientist at Central Petroleum. He's currently the Senior Geophysicist at Buru Energy, where he's responsible for seismic acquisition, processing, and part of the interpretation team. He's also responsible for potential field acquisition and more recently microseismic projects. His current research interests include extracting the most out of geophysical data, seismic technology, and airborne gravity radiometry.
Thanks, Simon. I guess today I was invited here by the committee to sort of present on Buru's work, and I guess Buru's been one of the big supporters of the Falcon technology. It's been something that's been extremely useful to us, and as you can see, we've got a pretty remote part of Western Australia to survey and to try and understand geologically. My boss, Eric Stryberg's a bit of a land grabber, and he decided that 250,000 square kilometres was the amount of Canning acreage that he was going to grab, and we sort of came into it, or I came into it in 2009, and well, what's a good way of trying to understand this acreage, high grade it, and use Buru's shareholders' money to the best advantage? And I sort of came across this airborne gravity technique, and it's like, well, maybe this might work. In the Canning, and I'll show you in just a minute, we've got some really interesting carbonate reef build-ups, and a lot of those have been dolomitised. Above these dolomite reefs, there's a nice package of silts and sands, and you get a nice density contrast at the top of these carbonate reefs and dolomitised reefs. I was like, well, yep, this might work. And so in 2011, I think we ran the first case study over Ungani, and at that same time we happened to be drilling Ungani 1, and we drilled a discovery there, and it's like, well, shit, this might work. And then we looked at the image, and fair enough, we could see the structure of the dolomite, and it's like, well, okay. So in 2013 I'll just move on a bit. Next slide. Usual disclaimer. So the contents here is I'll just do a quick introduction, and then three of my sort of key areas being Yakamunga and Ungani, Fitzroy Trough, Barbed Wire Terrace, and then I'll wrap up with some conclusions. So this is the Canning Basin. We're sitting here in the north of Western Australia, and it's a sort of a massive area. And this was the survey we ended up acquiring, and then we've stitched a little bit on last year in these areas through here. And it sort of runs about 400 kilometres and about 50 kilometres wide. And we're focused basically on the southern part of the Fitzroy Trough. So the Fitzroy Trough runs through here with sediment thicknesses up to 14 kilometres, mostly a clastic sedimentary pile, silts and sandstones. Nothing too exciting to get your teeth into. But right along here at drillable depths is some really interesting looking reefs that have been dolomitised. Ungani 1 penetrated these reefs, and we had great oil shows, and we managed to get a commercial flow of oil. So Ungani sits up here, and I've highlighted this as one of the areas to look at. So this on the Juggerah Terrace through here, and then some of the terraces run down through here, being the barbed wire terrace. And we'll see on the gravity data some of these interesting features that have popped out. And so we ran it all the way down here, and in particular this area is extremely remote, sits in the Great Sandy Desert. There's absolutely nothing, a smattering of seismic lines, a smattering of petroleum wells, mostly drilled in Wappet days and when Western mining were quite active in this area. So just moving on. So this is the gravity anomaly grid of Western Australia. I downloaded this and stuck the polygon over the top, and as you can see there's a bit of interest there, but it's fairly long wavelength. I probably could have done a first vertical derivative and made it look a bit nicer, but there isn't a lot of discrimination here at the sort of, you know, the long wavelength type things. We can see along here, through here, the Fenton Fault, Fitzroy Trough runs through in here. And just before I move on to the actual gravity data, I thought I'd just touch upon the stratigraphic column in the Canning Basin. And we're really starting in the Ordovician. There's a bit of interest in there, but it's pretty deep, it's pretty old, rocks are pretty tight. So most of the interest for Buru currently sits around the sort of the Devonian petroleum system and the Permo-Carboniferous petroleum system. Ungani sits in here in the Laurel Formation, and it's we've sort of discovered it a little bit by accident. We were drilling for tight gas, end up hitting a nice dolomitised carbonate with lots of really good oil shows. As sort of happens in the oil and gas industry, you just sometimes discover things by chance, and then that starts you off on a tangent. So that's what started all this, and then we've moved on and we've started to really delve into what's going on. Can we map it? Can we map it cost effectively? And the other problem we have in Western Australia is land access. It's not always easy to get a seismic survey where you want it. We've got the Fitzroy River, that's considered, you know, almost a no-go zone where we are. You know, running a seismic survey across there would be cause all sorts of ructions in environmental circles and with our traditional owner friends. And then we also have logistics, as Bjorn mentioned. You know, it's hard to get down there. It almost costs as much to get a seismic crew into a place than it does to actually run the survey. So Falcon became a really cost-effective tool for us to explore this area at a reasonable price. So just a quick representative cross-section of what sort of where our play types sit, and I've also put a sort of a response of the AGG across this type of terrain. So here we have Ungani, and it sits in the Laurel Formation through here. This major bounding fault onto our terrace areas through here, and we've got some interest in this area with some plays that we've tried to follow up on last year at this well called Tsanagi without too much success, a couple of little oil shows. And then in through here we have our tight gas play at Yallaroo, some interesting oil shows at Ungani North, and then we move back up onto the next terrace up and here was an old field discovered in the 1980s, I think by BHP at Pictou. And then over on the right hand side, which is the north, is where we drop into the Fitzroy Trough proper, and we sort of, you know, at the deepest point it's sort of speculated at 14 kilometres or so. So here we have the data that we collected from the Falcon system. So we started up here with our little case study at Ungani, and then in 2013 we acquired all this data up through here, and you can sort of immediately your eyes drawn to certain features along through here where you've got the Fenton Fault defining the platform areas to the south, and then the Fitzroy Trough up in through here, and all sorts of interesting looking faults that run through here. The Dummer Range Fault sort of you can see sneaking out through here, and then I've put the GD anomaly map in through here, which looks more like our Western Australian gravity map from earlier. So I've picked these three areas, one here at Ungani, because that's our sort of key area, our sort of our area of most exploration focus. We've shot a combined 3D seismic survey of over 1,000 square kilometres over that area now. Up through here in the barbed wire terrace area, because that's probably the most striking part of the gravity grid. And then I've also picked one area here right in the middle of the Fitzroy Trough where there isn't as much going on in the GDD image. It's quite bland, and I'll run on to that in just a minute. So our integrated interpretation workflow, CGG have conducted this mostly. Co-author Urian and Savelos have done a lot of work in terms of this. It was a massive project. It took over a year to interpret this, of almost Urian sitting in our office for months at a time. So we've done a big compilation of all the existing well and seismic data, shot the gravity data, and then we started a basement up interpretation. So we started the basement structure using the magnetic data, which was the 400 metre line spacing TMI data that the West Australian government flew. And we did a depth to basement estimation based on that. And then the intra-sedimentary interpretation was using the AGG. And this is where it sort of came into its own. The TMI image is basically transparent at the depths of investigation we were looking at, sort of the 1.5 to 3 kilometre depth. Whereas the AGG, you could pick out these nice density contrasts at the top of the carbonate reefs, particularly where they've been dolomitised. And we sort of estimate from our well density logs that there's sort of roughly about a 0.2 grams per cubic centimetre type of discrimination there, density contrast. And then we also looked at the surface and near surface structure using magnetics, Landsat geocover imagery, and then worked our way through to construction of geological cross sections using a sort of a 2.5D gravity modelling along these 2D seismic lines. And that wasn't always easy, particularly where we had some, you know, really old vintage data where the imaging was particularly poor. However, the old data had the longest profiles, so it was difficult, but I think it helped with the interpretation in the end. And then we also integrated some newly acquired seismic data that Buru got in 2014. And then I've just put this last one in here. This is all an iterative interpretation, and we're getting new data all the time, and new play concepts evolve, and we keep coming back to the Falcon data. It's such a rich data source, and it covers such a large area. We've hardly even scratched the surface at interpreting it, really. So this is our key area of Ungani. This was our 2011 data set, and we ran this at 500 metres north-south with 2 kilometre tie lines. And this is actually a filtered version. I've taken out the high frequency part of the image here. think it was Dave Moore did this particular interpretation. And you can see here, this is our Ungani well. It sits in here, and it corresponds pretty well to the structure of our sort of top dolomite level. And you can see these are sort of the faults that run through here and up in through here. And then on this side, this is a really interesting structure that we're exploring at the moment called Yakamunga. Looks pretty big, looks pretty interesting. Could be a game changer for Buru if it comes in. So this image is a depth image based on some 3D seismic we've shot recently, and the 3D seismic sort of runs up and around through here, and then the rest of the image is based on some 2D. And as you can see from the image before, there's some really good comparisons, particularly in the sort of the western part of the image, that we're picking up structural trends that look extremely similar to what we're seeing on the Falcon data. And that really gave us a lot of encouragement. That gave us the encouragement to spend a lot of money with Falcon, acquire a massive data set, and really try and understand what's going on in the southern Canning. It's a bit more complicated over on the eastern side with Yakamunga. We've got multiple unconformity levels. Things have changed quite rapidly in the space of probably 15 kilometres over here. So we're not quite as certain that what we're picking up on the Falcon, as you can see here, is representative of our dolomite level. There's some other rocks there that are muddling the picture, I guess, and we don't have enough stratigraphic well control to quite understand exactly what we're seeing on the Falcon over here. Yes, it's probably related somehow to the carbonates there, but we're getting deeper into the Fitzroy Trough, and something's changed, and we'll probably have to drill a well just to see what's going on. And then we can tie it back, use that knowledge to extrapolate to the rest of our gravity imaging, and then come up with some new concepts. So here we did some 2D modelling along a seismic line through Ungani. Ungani sits in here. It's about 2,000 metres, and we're just looking at the models through here. This is our sort of Ungani package, average densities of 2.7 grams per cubic centimetre. Oh, sorry, this one here, 2.75, and then some carbonates underneath. But above here, we've got the sort of the sedimentary package in through here, and this gives our contrast what we're picking up on the Falcon data. So an interesting thing, and the one thing that we were really interested in through here was any of this salt supported. There is evidence of salt in the Fitzroy Trough, drilled by Frome Rocks, and the gravity modelling really showed us that there was no possible way we could get salt under there and get this sort of response. So further 3D imaging has probably shown that it's supported by a faulted tilt block. So that was pretty good results from the Falcon, and that came out a couple of months after we flew it. So now I'll flip to the area that I showed in the Fitzroy Trough, and this was an interesting area. On the actual data that we flew, it's pretty bland. There isn't the same sort of density contrast that we're seeing on the terraces that we saw at Ungani and that we'll see on the barbed wire terrace. And I think this is because what we're seeing here is a large clastic wedge. We're not getting the reef build-ups that we're getting on the terraces. But what this did show me was that maybe we could look at something else that could help enhance what's going on here. So this was using the colour bar that we use for the large image, and given that it's 400 by 50 kilometres aerial extent, perhaps this wasn't the most appropriate area, most appropriate colour bar to use. So we changed it, and we just clipped it back to this area, changed the colour bar stretch, and already we're getting a lot more interesting features. But when we go to look at the actual maps that we've mapped from the seismic, and you can see the seismic lines through here, it's a pretty sparse database. What it's showing is that the structural picture is different to what we're seeing on the Falcon. And what we're seeing here is something a bit more stratigraphic rather than structural. So there's a lot more work to do here, and we haven't even touched the surface of this. I've just had a little play with it. Perhaps something we can investigate more. However, you know, it's trying to weigh up what is doable with the, you know, cost constraints that we've got in this current time period. And so this is looking at the deeper level. This is more on the Ungani dolomite type level. And we've got a sort of a high here that's not as representative as what we were seeing in the Ungani area before. So I've sort of have to scoot along quite quickly. Here we've got the barbed wire area that I highlighted before, and this is probably one of the most interesting areas of the Canning Basin. You know, it's got these huge density contrasts on the edge here. We're seeing the dropping into the Fitzroy Trough. Some really interesting, it's quite constrained down here by a lot of mineral holes, a lot of holes that were drilled by Western Mining. And what we did over on this side, Urine went through all of the data that was available, looked at all the seismic, and he started to assign, well, what sort of things are causing the gravity to get these sort of anomalies on the gravity map. And so he's gone through and he's very carefully mapped all the different carbonate sequences and tried to understand which ones are contributing more to the gravity signal through here. And that was quite useful. And we ended up, currently we're looking at dropping a lot of this acreage because we've just not able to explore everything through here. And the Falcon's been a really good tool in helping us decide which acreage we should keep and which acreage we're just going to have to let go. So this was some seismic lines through the area. You can see through here. This was some old 1984 data, 1985 data, sorry, and 1982 data that we stitched together. Here you can see that massive Fenton fault and the large sedimentary pile that we're getting through here. And up through here, we're struggling with imaging these carbonate bank edges in through here. Here, this was some data that we designed on the back of the Falcon data. So these were basically looked at and redesigned so we could get true dip seismic imaging across the faults. So here we've got the Fenton fault, the gravity profile on the top of that. There's our big sedimentary pile, Ordovician up against Permian through here. And then the basement's obviously a lot higher up through here, and the basement's well down below 5 seconds. And just another image just of that particular fault through here. So airborne gravity gradiometry surveys in the Canning Basin has provided a cost-effective way of exploring without incurring large costs. With complementary data such as seismic and well information, it can be effectively used as a high-grading tool. Pseudo-structural mapping with some important safeguards. Bureau's exploration department uses it on a daily basis to complement the sparse seismic control in order to fill in the geological blanks in a semi-guided fashion rather than relying on computer contouring of seismic lines. The Fitzroy Trough section with its large clastic wedge represents an area of the Canning without significant density contrast. However, through careful clipping of the area without artefact contamination, further clarity and contrast can increase the image quality and interpretability. The barbed wire terrace, with its higher density carbonate build-ups and potentially dolomitisation, provide the good density contrast which the Falcon instrument is good at imaging in the order of 0.2 grams per cubic centimetre. And we'll just move on a little bit. And given the difficulty of interpretation of seismic across the barbed wire terrace, the AGG provides invaluable insights into the distribution of the types of rock units and structures that would be encountered. However, proof of a commercial hydrocarbon system now lies with the drill bit. So I'd just like to say thanks to my co-authors, Yuri and Faith, for his hard work and dedication to interpretation, and Carlos Savelos for providing a lot of the images in this presentation, and to my company Buru for sponsoring me to come here. Thanks very much. Thanks, Simon. Cheers.
Okay, thank you very much, Tony, for that very interesting talk. And it's good to see some of the application of Falcon or AGG to in the hydrocarbon industry. Last but not least, we have Mike Enright from Rio Tinto. Mike graduated with honours in minerals and groundwater geophysics at Curtin University in 1996 under the wise tutelage of Ashton Mining's chief geophysicist Keith Jones. Mike quickly found himself providing geophysical support for Ashton Mining's global diamond exploration efforts. As a junior geophysicist, Mike was allocated all the fun jobs, including Mali, Guinea, Mauritania and Angola. His 5 years with Ashton Mining provided fantastic exposure to diamond exploration with a diverse range of geophysical methods and geological settings. In 2001, Rio Tinto acquired Ashton Mining, and Mike commenced geophysical support for Rio Tinto's diamonds and iron ore exploration programs in Africa. In 2005, Mike led Rio Tinto Exploration Africa-Eurasia region. Permanently returned to Australia and within 4 months found himself working for Rio Tinto Exploration Australasia region. Keeping up with this. For the last 11 years, Mike has been providing geophysical support to Rio Tinto Exploration Australasia's region exploration programs, which is diversified into copper, bauxite, coal, nickel and uranium. Mike feels very privileged to be part of Rio Tinto's wonderful and eclectic exploration team who constantly push the technical boundaries while ensuring there is some fun on the journey. Assume that last week was directed at CEO Lewis.
Wait.
Thank you, Mike. Thank you.
I assume I know how to...
Oh, sorry, you right?
I guess I am. What's you? Thanks everyone. Thanks Simon. My talk is a review of Heli-Falcon surveys for iron ore exploration in the Pilbara. In 2013, Rio Tinto Exploration conducted detailed Heli-Falcon airborne gravity gradiometer surveys over 2 advanced iron ore projects in the Pilbara region of WA. There's the Kadaidri Detrital project, which is situated in the Fortescue Valley, 130 kilometres northwest of Newman, and the Yandy Braid project, which is situated at the outwash of the Yandy Kugina and Marillana creeks, around 80 kilometres northwest of Newman. The Yandy Braid Channel Iron Deposit, or CID, is the downstream extension of the Yandy CID systems currently being mined by Rio Tinto and BHP Billiton. These surveys will provide an opportunity to investigate the value of AGG to iron ore exploration in the Pilbara and to discuss the most appropriate survey design when exploring for detrital iron deposits, channel iron deposits and bedded iron deposits. We'll start with the Yandy Braid project. Yandy Braid was a Rio Tinto exploration discovery in 2013 and was handed over to the business group. It had an inferred resources of 488 million tonnes at 61.7% and 238 million tonnes at 57.7%. Producing an accurate geological interpretation for the exploration program was challenging due to extensive cover, complex geology, wide space drilling
and magnetics dominated by remnants, which is common in most exploration projects and certainly remnants in the Pilbara. Heliphar can provide a consistent and new data layer to map structure and lithology and improve the geological interpretation. The survey was flown at 100-metre line spacing. Was this the most appropriate line spacing for the target? It's a good question, and I'm glad that you asked. Okay, my first plot. This slide provides an opportunity to evaluate the effect of AGG line spacing at Yanni Braid by comparing the original 100-metre line space data with reprocessed data at flight line spacings 200 and 400 metres. At this point, I'd like to state that the GDD and GD for this talk is equivalent of GZZ and GZ. Also, yes, also that the CGG reprocessed the original 100-metre line space data using the DEM, reprocessed the 100 to replicate 200 and 400-metre line space data. Sorry, I just lost me spot. Oops, sorry. Sorry, it's not working for me. Okay, back in business. They used the LiDAR from the 100-metre. They used the original LiDAR DEM for all of the processing. So I'll just explain the plot. So up the top, in the black profiles all the way through is ground gravity that's been upward continued and transformed into GDD. And the green profile is the original 100-metre line space. The blue is the 200, and the magenta is the 400. And each of the dots on the black profile, they're the gravity stations, and on the along the other profiles, or the AGG profiles, that's where the flight lines basically go into the page. Okay. The 100-metre line space GDD profile compares well with the ground gravity equivalent, except in the presence of a persistent and regular high-frequency noise component in the GDD, with a half wavelength of approximately 120 metres and an amplitude of approximately 25 ETVOS. The term noise is referring to the combination of instrument, processing, grid artefacts, and inherent near-surface geological variations. This regular high-frequency noise observed in the 100-metre line-space data is not present in the 200-metre line-spaced GDD profile. The 200-metre line-space data compares well with the ground gravity equivalent, which I'm referring to as reality for this talk. The 400-metre line-space GDD profile shows a significant degradation in resolution and accuracy. All three AGG profiles map the 500-metre half-wavelength Graben feature to the right, which I'll point out. So down here is a Graben feature, which we'll talk about more, which once again is perpendicular to these lines, and they all map it pretty well there. Though the AGG products deviate from the transformed ground gravity to the left of the plot. And I'll just point out at this stage, there's really no significant topography on this, in this area. So terrain corrections are not going to be the cause of any of this. So, you know, what I'm talking about here is in the 100, there's some deviation that seems to increase in the 200, and then by the 400, the correlation's really falling apart. And when we go to the next slide, I just want you to sort of focus in this area where they both correlate really well, and then by the 200, it's they're deviating. The 200 is sort of 40 ETVOS below, and then by the time you get up to here, the 400 metre is sort of 40 ETVOS above. And if you can just remember that area for the next plot. Now, if we take this particular profile and overlay it on grids, we have these plots. We can see the same ground gravity equivalent profile from the previous slide overlaid on the 100, 200 and 400 metre line space GD grids. The contours are consistent across all the grids. So there's your profile that we talked about on the last slide. There's your response from the Graben feature, which we'll talk about in a bit, and obviously the 100, 200, 400 metre grids. As would be expected, the 100 metre line space GDD grid has the greatest detail, although the previously mentioned consistent high frequency chatter is a significant distraction. The 200 metre line space GDD grid is less impacted by noise and effectively delineates the main geological structures. This includes the Graben feature we'll discuss in later slides and a parallel fault. I didn't mention the parallel fault, but this is parallel fault down here. And as I was talking about, that area to focus on before is basically this area here, and it's sort of interesting sort of how much it changes, in particular when you get to the 400 metre grid spacing. The 400 metre line spacing grid shows considerable offset in the location of key features. Also, the anomaly amplitudes vary considerably from those observed in the original 100 metre line space product. These offsets are significant in the context of exploration targeting. For the Andy Braid project, the 200 metre line space data is the preferred product for exploration, in my opinion. For this slide, we examine the previously mentioned Graben feature and the deposit more closely. We have a schematic geological cross-section of Yandy Braid deposit with associated GD and GDD profiles from the 100, 200 and 400 metre line space grids. The mineralisation response corresponds to a GD and GDD high, whereas the Graben structure, interpreted as being associated with the dissolution of carbonate units in the Dales Gorge and Macrae Shale units, correspond to a GD and GDD low. So I suppose the key features here is the red is outlining the extent of mineralisation. The Graben feature is schematically shown here with a bit of shale over the top, which is probably the main reason for the GDD low. And this is interpreted from this high as being the main source of mineralisation. I'll also point out that the CID is sitting in there under some alluvium. And of course over here we have the different profiles. The 200 metre line space profile has comparable geological signal to the 100 metre line space profile, but without the high frequency noise component. The 400 metre line space profile still detects the mineralisation and the Graben response, but there is migration in the GDD low by approximately 300 metres. This offset can be of concern for exploration. The Yandy Braid CID has no discernible gravity gradient response due to the dominant 40 plus ETVOS basement responses and its flat and tabular cross-sectional morphology as it broadens and thins on approach to the Fortescue Valley. Now we will focus on examining a 7 kilometre long section of the Yandy Braid channel iron deposit. So if we look at this plot, we have the original 100 metre line spaced GDD in the black. We have a long section through the CID channel, and this is a long section 3D cut through the 3D model that we made, and this is the densities that were required to make the red model response. The above plot illustrates the relationship between the gravity gradient and the geological model and an output derived by a constrained 3D inversion. The 3D lithological model is well constrained to the base of the CID from drilling and has been assigned average densities from downhole logging of drill holes. The 100 metre line space GDD grid profile shows the characteristic high frequency chatter. The longer wavelength signal is thought to reflect variations in basement lithology, although variations in the CID upper surface and offline 3D effects will have an impact. There is a poor correlation between CID thickness and gravity gradient, which is why I did the model in the first place. I thought we might have been able to do CID thickness. The modelling exercise was aimed at fitting the weaker, longer wavelength signal, and to this end the Joffre Biff density was allowed to vary heterogeneously. The output shows the unrealistic heterogeneity required in the Joffre Biff density to achieve even a relatively poor fit with the measured GDD data. The poor fit may partially be explained by variations in the alluvium that are not well understood. The poor result from the exercise highlights the challenge of quantitatively modelling gravity data at target scale in this environment. Now we will move to the Kadaidri detrital project. As mentioned, the Kadaidri detrital iron deposits are located along the southern margin of the Fortescue Valley, concealed beneath tens of metres of transported Cenozoic cover. Basement consists of the Whitnoon Formation's dolomite and shale. Kadaidri detrital iron deposit exploration is targeting AGG half wavelengths between 500 to 1200 metres. There is also a talk from Mirror Geoscience during the ASEG conference if you wish to learn more about the Kadaidri detrital iron ore project. Terrain variations for this project are negligible. Part of the Kadaidri Heli-Falcon survey overlaps with previously acquired ground gravity, providing another opportunity to investigate the Heli-Falcon data at 100, 200 and 400 metre line spacing. So up here we have the original data with the flight lines overlaid. We have the 200 metre with its lines, and we have the 400 metre. Over here I've upward continued the ground gravity and transformed to GDD. Please keep in mind the 500 to 1200 half wavelength target size for detrital exploration. The ground gravity data was acquired predominantly on a 100 by 400 metre grid, and as mentioned has been upward continued and transformed to GDD for comparison to AGG. This transformed ground gravity matches the character of the 200 metre flight line spaced Heli-Falcon. For me this indicates that for detrital iron ore exploration, a tighter line spacing for Heli-Falcon is required when comparing to what you need from ground gravity. The 100 metre Heli-Falcon data appears to have a high fidelity. However, the higher frequency noise component is a material distraction and complicates the interpretation. Also, the features parallel to flight direction not present in the ground gravity equivalent or 200 and 400 metre GDG data is a little of concern. And by that I mean these sort of things running this way, which is not in this data or this data or over here. Is it real? I'm not really sure. The 400 metre line space GDD product has lost substantial resolution with 500 to 1200 metre half wavelengths dominating the grid and consequently providing a much degraded tool for detrital targeting from the explorer's perspective. Now we'll focus on a section of one line of the ground gravity. So for the next slide, I'll be focusing in on that little section there. I think I'm 5, not too bad. Maybe I'll talk even slower. Okay, so I've just taken that section, and on the left plot we have the ground gravity transformed to GDD again, overlaid on the original 100 metre line space GDD grid profile. The 100 metre line space GDD profile aligns well with the ground gravity on the left of the profile and drifts away by the right of the profile. So what I mean is that by here they're very close and they do tend to drift apart over a reasonably short distance. This could have implications when undertaking inversions. On the right plot, we are viewing the original 100 metre line space GDD with the reprocessed 200 and 400 metre line space grid profiles. The selected gravity gradient line profiles show a 50 ETBOS 700 metre half wavelength anomaly. This is an ideal half wavelength when targeting detrital deposits, and all three profiles detect the anomaly. But, as mentioned on the previous slide, the 400 metre line space data is dominated by similar wavelength responses. So, once again, the 200 metre seems to be the best option. In conclusions, for the Yandy Braid bedded iron deposit, the GDD from the original 100 metre line space data provides little benefit over a similar product generated by reprocessing lines at 200 metre separation. However, there is significant loss in resolution and accuracy for the 400 metre line spacing. For the Yandy Braid channel iron deposit, the contributions from basement geology dominates the gravity gradient signal, but variations in the CID upper surface and offline 3D features also contribute. Also, the contributions from variations in regolith are not well understood. The 3D model study demonstrates the challenges of using AGG quantitatively when the true subsurface density distribution is poorly understood. Exploring for detrital iron deposits with AGG requires targeting half wavelengths between 500 to 1200 metres. A comparative study demonstrates ground gravity coverage at nominal 100 by 400 metre stations is comparable to 200 metre flight line spaced heli-falcon data. I'd just like to thank Rio Tinto Exploration, Growth and Innovation for their support in allowing me to present their data today. I'd also like to thank Mike Haley for his strong mentoring over the last 15 years. Mike always consistently encourages me to bring out my best effort in everything in life and make sure I enjoy every minute of it. I'd also like to thank CGG for reprocessing the heli-falcon data for this talk at 200 and 400 metre line spacing and providing technical input to it. Thank you.
I'll invite the speakers from that session back up onto the stage, and we'll welcome questions to any of the speakers. Yes.
Probably can make myself heard. I have a question for Louise. Did you realise that the red line on that graph was indeed for a single line at the normal caravan speed? And so I think that...
Well, and some of those results were from single lines, the test line results, for instance.
But I'm happy to see that you've pushed the
Right.
GPS noise down a little
Yes.
bit since then, so that's really
Yes.
good.
I have a question for Mike. You mentioned in the last slide that you had perhaps the regolith was not very well understood. I just wondered if some of that could be unconsolidated sediment or weathering or all sorts of variation in the surface, and do you think some of that has contributed to the 100 metre line spacing data set and then there's the point of separating noise from geological signal. Have you got any comments on that?
I think it definitely would, and I think CG would like to agree with me there. But I don't think that's all there is in it, since it dominates all of our survey, whether it's outcrop, regolith, we see the same sort of signal. So I'm sure it not being able to, I've done random grids, or I've been shown random grids, or had real, where you just make up random noise and then you go through the process of creating the product, and you will see that kind of same signature. So I think it's the wavelength filtering and the gridding process and somewhat unknown gravity, where the gravity response exactly is coming from. So maybe a combination of all.
I'd like to make a point about the digital terrain models or LiDAR sources. When LiDAR is processed, they're taking first returns and last returns, which will often represent the top of the canopy versus the top of your soil surface or ground surface. And I think us as an industry, we should push for both of those surfaces because it's collected at the highest resolution, and we can use the top of the canopy and the top of the soil or ground surface, both of those, to improve our products, rather than just rely on a lower resolution product to represent our canopy top.
Another question over here?
It was really a question to Michael, following on from Helen's question. With the noise that is clearly there, and you refer to as a distraction in the 100-metre line space data, have Rio Tinto and CGG made efforts to investigate that noise and remove it?
Well, maybe their new processing technique that they've just highlighted today might be worth throwing at it. But no, there hasn't been any sort of, well, I mean, I've shown my talk to them, but we haven't had a heart-to-heart on what we could do about it.
Any further questions?
Yeah, this is a question for Kit. Kit, excellent talk. I really like the idea of using these WW2 information and the additional satellite information to find water depth. Can you comment on what sort of the maximum water depth that you can extract from that approach?
For kimberlites in the slave, I did find a report, it's referenced in the full paper, that something around 20 meters, the relationship starts to break down. It's a direct relationship, and that it becomes less direct at about 20 meters. Fortunately, well, no, there are definitely lakes in the slave that are greater than 20 meters. I'm trying to think. Yeah, and they don't necessarily, not all those 20-meter holes are over kimberlites. So it starts to break down. Now, I didn't, in my rushed, garbled presentation, based on the suspicion we had of that one at that arm, east arm. Now, I did have lakes over to the east that I didn't bother showing, but so we felt, okay, anything over 10 meters, we're going to, if we have a target at anything over 10 meters of optical bathymetry, we have that designated for doing conventional sonar or conventional bathymetry, whether that's through auger on the ice, at least spot checking in the winter, or in the summer. Nothing is being drilled, unfortunately. Since we did that work, that's about when everything really went to its current status. Nothing's being followed. We haven't been able to get back on the property just because of no budget.
So I had a question for Kit as well, which was, you showed an anomaly which before you did the bathymetric correction was a clear, strong circular low. Then after you did bathymetric correction, it was quite a weak low. So it seems to me that it's, that doesn't necessarily mean it's not a kimberlite, or it doesn't necessarily change the priority of the target, because it just might have been that that crack has been scraped away by the eye. So I just wondered whether it had changed the priority of that target or not.
It did. What I didn't mention, again, we took all our targets that, and that one was one of them, that sort of remained. We ran them through a unconstrained modeling using Voxy, both magnetics and, well, primarily gravity gradiometry. Those are all modeled, and that's all available on the corporate presentation. And if we didn't have roots, we would model it. And well, if there was a tooth or a root, then okay, this remains to be a good target, or at least a target. If it just disappears, if it's just then we downgraded it. That particular one was probably going to remain just because it's at the head of the train, and it's one of the. But
Well, and you said it had a nice kimberlite, yeah.
yeah.
I'll try and ask a question for everyone to have a crack at, and that's the noise. I think if we're trying to look at Kit's talk, Tony didn't talk about it very much, but Mike certainly did, especially with the Falcon. I think I wasn't very happy with, just personally, with the treatment of noise for Falcon, and it's not that hard to come up with a QC measure which everyone can use, which is sort of a bit better than what I've seen today. So has anyone got any ideas, or they'd like to contribute or talk about how do we quantify noise for gravity gradiometry that everyone is happy with? That's more or less the question, because I reckon you can do a hell of a lot better than what I saw today.
Is that a question or?
That's a question.
Okay, well, speaking for myself on the Kachika Trough survey, we used Mark, it's your formula.
Difference noise?
No, not the difference noise. Well, we had two things noise. One was on the terrain model. So you had that paper. Yes. Yeah, so we, based on that, on the uncertainties of our terrain model, we came up with about 33 ETFOS noise. That was, and we're looking for a signal of 30 to 50 ETFOS at most. So we think, oh, this is, and that's when we got this, and then we started going, well, why? How can we fix this? And we devolved or convolved into that processing of the data. Ultimately, and then we got onto the transformation, and we started trying to look at the real and imaginary, or the difference in the transformations with a single value. But Des, I don't think that's really answering what you want.
No, it's just I want to tease everyone to do better.
If I could make one comment, that it's also not that straightforward, because for a Yandy Braid project, the amplitude of that sort of oscillating changed as compared to the much quieter area where the signals weren't as strong. So it's definitely dependent, from what I can see, on the strength of the signal that you're getting. So just saying that you're going to have a noise envelope for everything is really, I think, a little bit unrealistic as to what seems to be getting out of the product. So it has to be dependent on the signal. So it has to be a signal to noise, I think.
What I would add that, and again, I didn't mention it when I was talking, just looking at the measurement noise of whether it was ARC and now Austin Bridgeporth or Bell or the Falcon system, merely looking at the instrument noise doesn't necessarily tell us much in terms of interpretation. I'm not answering the question, Des. I don't know how to go any further.
I'm going to make a few comments. So one it's just continuing Kit's point there. I think it's important, certainly for the Falcon system, I can't speak for the other systems, you know, that report of instrument noise that we make on our surveys is a QC to check that the instrument's performing the way it should be. So Des, you make a very good point, and Kit makes the same point. That doesn't tell you the whole story. That's just, you know, a QC tool designed for a particular purpose. And then the other thing I wanted to say is there's kind of a hidden story here, which I think is worth telling. So that second example that Kit showed, and you know, obviously, you know, at CG we're looking at the problems that they're seeing in the data, and it's a serious concern to us. And Kit mentioned that Steve Saul did a huge amount of work on that, on the data processing side. So in my talk, you know, the authors there were Chan Yu, myself and Bill, and I said, well, Bill did the software stuff, and I kind of left it at that. But actually there was a significant evolution in our equivalent source processing, which is essentially thanks to these guys, because they just said, this is no good, you know, you've got to fix this. And that was basically what Bill did. So, I mean, it was a combination of what was in the software and the way we were using the software, and both of those things basically came back to the fact that none of this had ever been intended to be used in an aircraft that was flying those kinds of drapes. You know, I mean, the helicopter pilots are doing these weird things with the helicopter to make sure he doesn't hit trees as he climbs this mountain. And the processing software hadn't really been designed for that purpose, and we had to make a number of changes to improve it. So I think you know, one of the consequences, we have ended up with a much better product, and as I think you saw from my talk, that that has, you know, paid off in those extreme rugged terrains. That doesn't answer all your question, but good on you for teasing out some more information here.
Okay. If we can just thank sorry, we're going to have to wrap up. Just thanks the speakers for this session one more time. We also have some gifts for the poster presenters. So if you've got a poster out there, if you just come forward now, and we'll give you the same gifts that the speakers have got. If you want any words of wisdom, Mark?
There's no more wisdom. All the wisdom has been already given. But maybe as they're coming up, I just will take the time to thank everybody once again for coming here. Thank everybody for their excellent questions and feedback, and thanks once again to the speakers and presenters.